wabarakatuh, and very good afternoon to everyone. First and foremost, I would like to thank everyone, especially students who are able to attend this class, this online e-class organized by Digital Classroom Kolej Matrikulasi Negeri Sembilan. My name is Madam Azlina binti Ismail, a lecturer from Kmns. And I have a colleague of mine, Madam Nik Abibahtun, who is a chemistry lecturer from Kolej Matrikulasi Negeri Sembilan, who will be teaching a selected topic for chemistry. Okay, so without further delay, I would like to invite Madam Nik Abibahtun to deliver the class. Okay.
Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and a very good afternoon to all. Thank you Madam Azlina as our moderator for e-class chemistry today. Welcome to all students to e-class chemistry today. So let me introduce myself first. My name is Madam Nik Abibahtun, chemistry lecturer from Negeri Sembilan Matriculation College. Without further delay, let us start our e-class for today. So today, I will choose topic 2, Thermochemistry, and subtopic 2.4, Born-Haber Cycle. So I choose this topic because we already learned this topic around November 2019, which is last year. So means that it already passed a few months. Therefore, it's better for us to have a bit of revision for this topic for our PSPM session, semester 2 session 2019-2020. So topic 2, thermochemistry. In this chapter, we have 4 subtopics, which is 2.1, concept of enthalpy, 2.2, calorimetry, 2.3, Hess's law, 2.4, Born-Haber cycle, which is our focus for today. So, learning outcome for today that we're going to try to achieve, we try to construct the Born-Haber cycle for simple ionic solid using energy cycle diagram and energy level diagram. Another one, we're going to calculate the enthalpy changes using Born-Haber cycle. So for Born-Haber cycle, Born-Haber cycle is an energy cycle for ionic compounds. It connects enthalpy of formation, which may be determined experimentally, with lattice energy, which cannot be determined experimentally. Therefore, one of the major applications of Born-Haber cycle is in the determination of lattice energy. Sometimes Born-Haber cycle are drawn so that the relative length of the arrow is proportional to the energy change involved. So for endothermic reaction, arrow will be pointing up with a positive value, while the exothermic reaction, arrow will be pointing down with a negative value. So for this diagram, we call as enthalpy diagram. Therefore, we can say that Born-Haber cycle, you can show it by using these two types, which is energy cycle diagram or enthalpy diagram. So on my left is the energy cycle diagram, while on the right is enthalpy diagram. We're going to look through all these two during this session. In calculation of the data from the Born-Haber cycle, we need to apply the Hess's law. So you still remember Hess's law? Don't worry. Let us look at the definition first. So Hess's law states that when reactants are converted to product, the change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. So we look at the diagram given here. We have path 1 and path 2. So we can see that at path 1, we only have one way, while from the path 2, we'll have two ways. Means that A will change to C first, after that will change to B. Therefore, according to the Hess's law, path 1 is equal to path 2, so we use the enthalpy. Delta H is referred to enthalpy. We refer to the enthalpy, we write in the path enthalpy number 3 equals to enthalpy number 1 plus with enthalpy number 2. So we look at the usage of the Hess's law. We use it to calculate the enthalpy change which cannot be determined by experiment. So what we're going to look today. And another one, calculation involves two methods, which is algebraic method and energy cycle method. For this one, you already look at the previous subtopic, which is 2.3. In able to construct Born-Haber cycle, we need to recall back the definition of the enthalpy that involved in Born-Haber cycle. So we start to look at the enthalpy, the standard enthalpy of reaction at the standard condition, which is constant pressure of 1 atm and temperature 298 Kelvin. The first one that you have to remember, the definition of the enthalpy of formation, which is heat change when 1 mole of compound form from its element in their most stable state under standard condition. After that, enthalpy of atomization, heat absorbed when 1 mole of gaseous atom are formed from its element in its most stable state under standard condition. Ionization energy, the minimum amount of energy required to remove 1 mole of electron from 1 mole of gaseous neutral atom to form 1 mole of gaseous positive ion. Electron affinity, heat change when 1 mole of electron is added to 1 mole of gaseous neutral atom to form 1 mole of gaseous negative ion. And last one, lattice energy, the definition is heat release when 1 mole of ionic solid formed from its constituent gaseous ion. Okay, from all of this definition of enthalpy, we can use the first letter each of the enthalpy to help us as a guide in construct Born-Haber cycle. What is it? So we look at the formation, the in front letter is F, atomization A, ionization energy I, electron affinity E, while lattice energy is L. Therefore, we can use this acronym to guide us to construct Born-Haber cycle after this. So it doesn't matter how you want to pronounce this one, F-A-I-E-L, Fa'il, Fa'il, because in chemistry, we don't have the oral test. As long as you can remember it, then it will be okay. So let us proceed with example 1. So we read first the question. So given enthalpy of formation of sodium chloride, from the data in the table below, construct Born-Haber cycle for the formation of sodium chloride, and B, calculate the lattice energy for sodium chloride. So we will use this acronym. We will use the acronym that we looked just now. Okay, so from the information given to us, all of the enthalpy, formation, atomization, ionization energy, electron affinity, and lattice energy of the sodium chloride. So most of the students able to write the equation, but equation right is not according to the definition. That's why we recall just now the definition of the enthalpy. So now let us try to write back the equation according to the definition. We start with enthalpy of formation. Heat change when 1 mole of compound form from its element in their most stable state under standard condition. So we look at here, 1 mole of compound form from its element at their most stable state under standard condition. So at most stable state, sodium exists as solid At most stable state, chlorine will exist as a gas. So we balance it to get 1 mole of sodium chloride. Second one, enthalpy of atomization. We must write the equation according to the definition. Heat absorbed when 1 mole of gaseous atom are formed from its element in its most stable state under standard condition. So for sodium, its most stable state is solid, so sodium solid will produce 1 mole of gaseous atom. Next, enthalpy for the atomization of chlorine. So chlorine, the most stable state is Cl2 gas. So we'll produce 1 mole of gaseous atom, Cl gas. Then we'll try to balance it, or write it half of Cl2. Next, the ionization energy. So here we have ionization energy for sodium. According to the definition, the minimum amount of energy required to remove 1 mole of electron from 1 mole of gaseous neutral atom to form 1 mole of gaseous positive ion. So we look at the equation that show here. Sodium remove 1 mole of electron, then will form 1 mole of gaseous positive ion. Next is electron affinity. Heat change when 1 mole of electron is added to 1 mole of gaseous neutral atom to form 1 mole of gaseous negative ion. So we look at the equation. 1 mole of electron is added to 1 mole of gaseous neutral atom to form 1 mole of gaseous negative ion. And last one, lattice energy, heat released when 1 mole of ionic solid formed from its constituent gaseous ion. From its constituent gaseous ion, sodium ion gas, chloride ion gas will produce 1 mole of ionic solid. So here we already recall back to write the chemical equation according to the definition of enthalpy. So now we will construct Born-Haber cycle. So by using the acronym that we looked just now, we're going to construct the energy cycle first. After that, I will show you how to construct the enthalpy diagram. For the energy cycle diagram, always start with the enthalpy of formation at top of your cycle. So we look at here, enthalpy of formation at top of your cycle. Since we already write the equation just now, so we can just take it and write it as our top of our cycle. And make sure you write together with all of the phases and the value of enthalpy. Value of enthalpy, you can write it on top of arrow. And the unit you write in the cycle, enough for the kilojoule. So now we settle with the formation. Next, look at the acronym is A. A is atomization. So for the atomization of sodium, sodium solid will change to gas. So enthalpy number 2, positive 108 kilojoule for enthalpy of atomization sodium. Okay, after that, we also have the atomization of chlorine. So atomization of chlorine, we look at the equation of atomization that we write just now. Half Cl2 gas will produce 1 mole of chlorine gas. So in the cycle, at the enthalpy of formation is already half Cl2. So we can just directly write Cl gas together with the value of enthalpy. So we finish with the atomization. Next, we have I which is the ionization energy. So with ionization energy for the sodium, from gas will change to the sodium ion gas. Then we write the value of enthalpy, positive 500 kilojoule. Finish with the ionization energy. Then proceed with the electron affinity. E, electron affinity. So electron affinity, chlorine gas produce Cl minus gas. The value of enthalpy according to the question given, negative 364 kilojoule. So last one, to complete our cycle, we look at here, sodium gas plus, make sure you write the plus, with the chlorine gas, connect it until the sodium chloride solid here, then label it as lattice energy. Therefore, we already complete our energy cycle diagram. So, while you complete your energy cycle diagram, check your phases, check your unit at your enthalpy, and check your label for each of the enthalpy. You can write the label of each enthalpy according to the number 1, 2, 3, 4, 5, and so on. Doesn't matter. Or if you want to write it as formation, atomization, electron affinity, ionization energy, also can. Next, we're going to apply the Hess's law. According to the Hess's law that we looked just now, enthalpy change of the reaction is the same whether the reaction takes place in one step or in a series of steps. A series of steps means that we're going to sum all of these enthalpy below here, equal to the enthalpy of formation up here. So substitute all of the value from the cycle. So I think you don't have a problem to substitute the value. Then from the value that you substitute, question wants you to calculate the lattice energy. So lattice energy equals to negative 777 kilojoule per mole. So now we already answered both of the question, construct the Born-Haber cycle, and another one we answer to calculate the lattice energy. So this one, another one, we have to look at the enthalpy diagram. So this one also can be shown as another Born-Haber cycle. So for enthalpy diagram, we have the energy that must be labeled. We'll start from energy equals to 0. This positive and negative is for your guideline only. It don't have to be right in your answer. So we'll start from the energy equals to 0. Same, we're going to use the acronym that we looked just now, FAIENL. So we'll start from the formation first. So formation, sodium solid plus half Cl2 gas will produce sodium chloride solid. According to the value enthalpy given, the value of enthalpy given for formation is negative. So when the value of enthalpy given is negative, in the enthalpy diagram, arrow must pointing down. Okay, and then we label the value of the enthalpy. Number 1 equals to the value of a given negative 411 kilojoule. So we finish with the formation. Next, we'll proceed with the atomization. So we'll start with the atomization of sodium. So atomization of sodium, from sodium solid change to gas. And then write your arrow pointing up with the value of the enthalpy, positive 108 kilojoule. Our arrow is pointing up because the value of enthalpy is positive 108 kilojoule. Okay, we can look at here, the changes only occur for the sodium, but the chlorine is still the same. Don't worry, just copy it. Next, we'll proceed with the atomization of chlorine. So atomization of chlorine, half Cl2 gas, will produce 1 mole of gaseous atom, chlorine gas. So write the value of enthalpy, enthalpy of the atomization of chlorine, positive 122 kilojoule. And then look at the sodium. Sodium, no changes. Again, don't worry. Just copy it. Just copy it back. So we settle with the atomization of chlorine. Next, we're going to proceed with first ionization energy for sodium. So we already look at the how to write the equation according to the enthalpy just now. According to the definition, when you write the equation in the first ionization energy, we'll have the electron in the equation. For enthalpy diagram, we must write the electron. It's different from the energy cycle just now. We don't have to write the electron. But in this enthalpy diagram, we need to write this electron. Okay, write the value of the enthalpy according to given in the question. Enthalpy number 4, positive 500 kilojoule. Okay, then electron affinity. So electron affinity is the changes occur for the chlorine. So we write the equation here for the chlorine, Cl gas will change to Cl minus gas. But for the sodium ion remain the same. We can see here no more electron. Why there's no more electron? Because in the electron affinity just now, we gain one of the electron. When we gain one of the electron, that electron will be cancelled out the electron we have here. Therefore, the next equation, no more electron. Don't forget to write the arrow pointing down. Pointing down again because the value of the enthalpy is negative. Then, complete your cycle by connect the sodium ion gas with the chloride gas to the sodium chloride solid. So label lattice energy. Okay, so now we already finished with the enthalpy diagram. It looks easy, but try to write it first. Then you will know whether is it easy or not. So up to you which of the Born-Haber cycle you want to show. You can use both, either one, either energy cycle diagram or enthalpy diagram. Okay, we're going to apply the Hess's law also. So by using the Hess's law, the same enthalpy of the reaction is the same whether it take place in one step or in a series of steps. Then we just substitute the value that we write in the enthalpy diagram just now. Then we're able to calculate the value of lattice energy. So we'll get the same answer, negative 777 kilojoule per mole. So final answer, make sure together with the unit kilojoule per mole. Okay, so we finished already for the example 1. So this example 1, we want to calculate the lattice energy and construct Born-Haber cycle. So let us try to look at the example 2. Example 2, draw Born-Haber cycle for the formation of magnesium chloride from magnesium metal and chlorine gas. Calculate the enthalpy of formation magnesium chloride. Example 1 just now, we look how to calculate the lattice energy. But this example 2, we want to look at how to calculate the enthalpy of formation magnesium chloride. The same value of the enthalpy were given to us, only give the name of the enthalpy, not the equation. So again, you should be able to write the equation by yourself according to the enthalpy definition of the enthalpy. Okay, according to the definition of the enthalpy, we should able to write all of these equations. Practice will make you perfect. Make sure always practice to write the correct equation according to the definition. I will proceed to show to you how to construct Born-Haber cycle from the data given. So I show to you the first one is energy cycle diagram first. We're going to use the same acronym like we do just now. So we're going to start with the enthalpy of formation magnesium chloride. This enthalpy of formation magnesium chloride does not given to us the value. That's why we have to calculate the value of enthalpy of formation magnesium chloride. Okay. And then we proceed with the A, atomization. So we have the atomization of the sodium here. Magnesium from solid change to gas. We write the value of enthalpy according to the given in the equation, positive 149 kilojoule. And then we also have the atomization for the chlorine. But for the chlorine, something not right here. In the equation, in the cycle, we have Cl2. But according to the definition just now, we write the equation, it's half Cl2. So what we have to do? We want it Cl2. So we have to time the equation by 2. Yes. So times the equation by 2, then you will get 2Cl gas. While you multiply your equation by 2, your value of enthalpy should also times by 2 here. Okay? So we finish with the atomization, then ionization energy. So ionization energy for the magnesium gas, produce a magnesium ion gas with the value given to us according to the equation, positive 740 kilojoule. Magnesium will have another ionization energy, which is second ionization energy. So we're going to just continue, still just continue the second ionization energy. So continue the second ionization energy will produce to you Mg2 plus gas. And write the value of the enthalpy, positive 1456 kilojoule. Okay, as we look just now, in the enthalpy diagram, we need to consider the electron. But in this energy cycle diagram, no need to write the electron. Okay, then we proceed with the electron affinity. Electron affinity will occur for the chlorine. Same goes to the atomization just now. Electron affinity, we need 2Cl gas. But according to the definition just now, only 1 mole of chlorine gas. So what we have to do? Again, we should times the equation by 2, and we also times the value of enthalpy by 2. So we'll get the product is 2Cl minus gas. Since the magnesium have 2 ionization energy, 1 and 2, they'll have a big gap here. So when they have a big gap here, for the chlorine, you just make it the arrow longer. Then you can produce the magnesium ion with 1 line. And complete your cycle by connect your lattice energy from the magnesium ion with the chloride ion will produce MgCl2 solid. Then label the value of the enthalpy, negative 3933 kilojoule. Okay, we finished construct the energy cycle diagram. Now, our next question, we have to calculate the enthalpy of formation magnesium chloride. We'll still apply the Hess's law. So apply the Hess's law. Enthalpy change of the reaction is the same, whether the reaction takes place in one step or in a series of steps. So a series of steps, we're going to sum all of the value of the enthalpy, enable to get the value of enthalpy of formation. So enthalpy of formation equals to, substitute all of the value enthalpy into the formula, then we get the value of enthalpy formation equals to negative 2084 kilojoule per mole. Again, the unit is kilojoule per mole. Okay, check back your cycle. Make sure complete with the phases, complete with the unit, complete with the label. Then your energy cycle is done. Next, we look at the enthalpy diagram. Again, we draw its energy arrow. We'll start from the energy equals to 0. Positive and negative show just as your guideline. No need to write as your answer. We'll start with the formation of magnesium chloride. Magnesium solid plus chlorine gas produce magnesium chloride solid. So arrow going down. Why? Why the arrow going down? Yes, because we'll forget the value of enthalpy of formation negative. Okay, then we'll proceed with the atomization of magnesium. Atomization of magnesium from solid to gas. Then write the value of enthalpy given 149 kilojoule. The value of enthalpy given is positive. That's why the arrow is pointing up. Okay, the changes only occur at the magnesium, while the chlorine is the same. Don't worry, just copy it back. So we settle with the atomization. Okay, then this one is ionization energy for the magnesium. Ionization energy of the magnesium from magnesium gas will produce magnesium ion together with the electron. Then label the value of the enthalpy positive 740 kilojoule. Finish with the ionization energy. Apa ni? Patutnya tick kat situ. Okay, next. We proceed with the second ionization energy of magnesium. So second ionization energy of magnesium, we can see here we have 2 electrons from the equation. And chlorine gas is the same. No changes, just copy it back. Then write the value of the enthalpy for second ionization energy of magnesium. Okay, then the changes occur between, we proceed with the electron affinity. Electron affinity from chlorine gas will produce atomization of the chlorine. Cl2 gas will produce 2Cl gas. We already looked this one just now, why we should time it by 2. So make sure you know whether it have to times by 2 or not. So times the equation by 2, you must also times the value of enthalpy by 2. Okay, then proceed with the arrow pointing down. When you look at the value, then you will know whether you have to pointing up or pointing down. Look at the value first. Okay, pointing down because the value of the electron affinity for the chlorine is negative. And again, we look at here, at equation up here, we have 2 electrons, but the next equation, no more electron because it cancel with electron from the electron affinity. Okay, so the value is negative. 369 kilojoule should be times by 2 as what we looked just now. So we complete our enthalpy diagram, finish it with the lattice energy, then label the value of lattice energy, negative 3933 kilojoule. Okay, we finish already with the enthalpy diagram. It's look easy, right? Practice, practice, practice will make you perfect. Okay, so we look at the applying the Hess's law. So applying the Hess's law, we substitute the value into the formula. Then we'll get the value of the enthalpy formation. Same answer, negative 2084 kilojoule per mole. Okay, so we're still using the acronym FAIEL to help us construct the Born-Haber cycle. Okay, last one for today. We look at this exercise. So for this exercise, we read the question first. The more chemical data for the formation of sodium oxide, Na2O, is given in the table below. So with the value of the enthalpy given to us, we have to construct Born-Haber cycle for the sodium oxide. And then we have to calculate the enthalpy of atomization of sodium. Different, right? Just now we look at the example. Example 1, calculate the lattice energy. Example 2, calculate the enthalpy of formation. But this time as our exercise, we try to calculate the enthalpy of atomization of sodium. Okay? Again, you should be able to write the equation according to the definition. Practice to remember all of this definition and write the equation correctly. Then, going to construct the energy cycle, Born-Haber cycle. So we start with the formation of sodium oxide. The formation of sodium oxide, given to us the value is negative 414 kilojoule. So we just copy the value of the enthalpy and write the equation top of your cycle. Okay, next, we proceed with the atomization. So atomization, we'll start with the sodium. So when we look at the atomization of the sodium, according to the equation, according to definition, it's 1 mole will produce 1 mole. But in our cycle, 2 mole. So same goes to what we look in exercise 2 just now. We should time it by 2 in order to get 2 sodium. So when we time the equation by 2, the value of enthalpy also should be timed by 2. Since question wants us to calculate the value of atomization of sodium, then we should write 2x. Okay? Why 2x? Because we timed it by 2. Then we'll produce to you 2 sodium gas, 2 mole of sodium gas. Okay, then we're going to proceed with the atomization of oxygen. So atomization of oxygen in the cycle, half O2. According to the definition, half O2 also. So easy, we just write it 1 mole of oxygen gas produced. Write the value of the enthalpy of atomization together with the unit kilojoule. Okay. Then we proceed with the ionization energy. So ionization energy, 2 mole of sodium gas will produce 2 mole of sodium ion gas. But look at here, according to the definition, 1 mole to 1 mole. Again, when we times the equation by 2, our enthalpy also should be timed by 2. Then we'll proceed with E, electron affinity. Electron affinity, oxygen gas will gain 1 mole of electron, then produce to you the oxygen gas. So enthalpy, the value of enthalpy given, negative 141 kilojoule. Okay, for oxygen, we have 2 electron affinity. So first and second. So we proceed with the second electron affinity of oxygen. Second electron affinity of oxygen will produce O2 gas. Then write the value of enthalpy according to the equation, 750 kilojoule. Same goes to exercise example 2 just now. Sodium have only one ionization energy, while the electron affinity of oxygen we have 2. So try to adjust your cycle, your arrow here, make it longer so we can get the equation for the lattice energy cantik. So we connect it to complete our cycle for lattice energy. So enthalpy for the lattice energy of sodium oxide is negative 2478 kilojoule. So we finish with construct the Born-Haber cycle, energy cycle diagram. Check your phase, check your unit for your each enthalpy, and check your label for your enthalpy. Again, we're going to apply the Hess's law to calculate the enthalpy of atomization of sodium. So applying the Hess's law, according to the Hess's law, substitute all of the value from the cycle, then we should get the value of enthalpy of atomization sodium equals to 107 kilojoule per mole. So you can also write it back, enthalpy of atomization of sodium, positive 107 kilojoule per mole. Okay. Last one, enthalpy diagram for the same equation. So we'll start from the energy equals to 0. When we look at the data for this equation, it quite fluctuate, not as what we're doing in example 1 and example 2. So this enthalpy diagram will be up, will be down, and then up, down, up. So sketch it first. If you want to use this enthalpy diagram, sketch roughly first, whether you have to going up first, going down, then make it clear the arrow, then will be okay for you to construct the enthalpy diagram. Okay, so we start with enthalpy of formation. So enthalpy of formation for the sodium oxide, look at here, I make it longer. Since I already sketched, so I know I need to make it longer. So you can see here, it's different from the example 2 just now. Example 2 and example 1. The arrow is not very long. So the line here is not very long. But for this question, it's quite long because I already sketched and I know I need a space for this. Okay. Then proceed with the write the equation for the formation and produce sodium oxide solid. Write the value of the enthalpy for the formation, negative 414 kilojoule. So going down, arrow going down, just now we already know because the value of the enthalpy is negative. Settle with the formation, we proceed with the atomization. What the question want? Enthalpy of atomization. So enthalpy of atomization, 2 mole of sodium solid will produce 2 mole of sodium gas. We already looked just now why we have 2 here. Okay, so same for this enthalpy diagram, we write 2x. So no changes for the oxygen, no problem, just copy it back. Okay, next, we'll proceed with the ionization energy for sodium. Ionization energy, first ionization energy for the sodium. So we can see here from the sodium gas, produce sodium ion with 2 electrons. For the oxygen, still no changes, no problem, just copy it back. Okay, make sure your enthalpy for the ionization energy also times by 2. Proceed the enthalpy diagram. From the half oxygen will produce oxygen gas. This is enthalpy of atomization. So label the value of enthalpy number 2 equals to positive 249 kilojoule. Okay, there are no changes for the sodium part, no problem. Just copy it back. Then, when we look at the value of the electron affinity of oxygen, first electron affinity of oxygen is negative. So the arrow will be going down. So the arrow going down, look at the number of electron. 2 electron. For the first electron affinity of oxygen, we gain 1 electron. So at the next equation, will remain the 1 electron in the equation. It's different from the example 1, example 2 just now, right? Example 1, example 2, no more electron. But this one, we still have another 1 electron. Okay, this one is for the first electron affinity. Okay, then we proceed with the second electron affinity. So when we proceed with the second electron affinity, going up. So when going up, because the value of enthalpy given to us is positive. So gain 1 mole of electron will produce to you O2 minus gas. So now no more electron because it will be cancelled out with the electron added during the electron affinity. So no more electron. Complete our cycle by connect the arrow to the lattice energy from the 2 and A plus gas plus O2 minus gas will produce sodium oxide sodium. So this is your lattice energy. Write the value of the lattice energy, negative 2478 kilojoule. Okay, so you finish already construct the enthalpy diagram. Check back your phases. Check back your equation, whether it's correct or not. And applying the Hess's law to answer the next question, enthalpy of atomization of sodium. So substitute all of the value from the enthalpy diagram that we do just now. Then we get the enthalpy of atomization sodium equals to 107 kilojoule per mole. Again, the final answer unit is kilojoule per mole. You can also write it back as what we've done previously. Enthalpy of atomization of sodium, positive 107 kilojoule per mole. So, finish with the exercise means that finish. So, let us look at the summary. So, what we already looked just now, we look at the Born-Haber cycle. So, in Born-Haber cycle, you can construct it whether energy cycle or enthalpy diagram. It's up to you which one you want. Both of it are accepted in the exam. And we apply the acronym to construct the Born-Haber cycle. We use the acronym FAIEL, FAIL, doesn't matter. Check all the phases and unit right correctly in the Born-Haber cycle. And we apply the Hess's law in the calculation. And lastly, make sure you check your final answer with the correct unit. I think that's all from me for the thermochemistry. For all of you students, keep study and make sure we'll grab the 4 flat for our PSPM. So stay home, stay safe, make sure have a prevention during this phenomena of COVID-19. Make sure all of the students back for our PSPM, inshallah. That's all from me. So I pass back to moderator, Madam Azlina. Thank you.
Okay, Alhamdulillah. Thank you to Madam Ni Abi Batun for detailed explanation of Born-Haber cycle. Congratulations, and I really interested with the using of FAIL acronym that was introduced by the Madam Ni Abi Batun. Hopefully it will be very useful to all students. And also thank you for Madam Ni for sharing the way to tackle the answer for some example of question regarding to this subtopic. Once again, on behalf of Digital Classroom, Kolej Matrikulasi Negeri Sembilan, thank you to Madam Ni Abi Batun for joining us today, and also thank you to all students for your attention. Okay, that's all. Thank you. Assalamualaikum warahmatullahi wabarakatuh.